Okay, let's jam. This one, you got to put your thinking caps on. If you want to put 3.2, we're going to do something called a logarithmic function. It's cool. It's awesome. And we're going to try to unconfuse you. Okay.
If you don't have a brain, you're not in danger. So you stay chill.
All right, let's see. So what we have to think about is this right here. This definition of a logarithmic function is kind of unusual, or you can say that it's funky, okay? So we got to think about some stuff first. So don't write this down, kind of think with me. Just write down 2.1 logarithmic functions and their graphs. That's all you need to write down. The rest of it, put your thinking caps on. Let's jam. So we have, this is all about opposites, opposite operations. We're good? So we're going to take a look at a few things here, and then we'll define the log function. Okay, first things first, I'm going to define something that's adding. So y is equal to 2, or y is equal to x plus 2. Talk to me, that is an addition function, is that right? What do we, if we want to take the, oh, let's go over here real quick here. We've got to make a table, maybe not that far away here. So if you go x and y like this, right? Let's make 1, 2, let's put in 3 values here. I'm going to put a value in for 0. Answer, everybody, is 2. I'm going to put a, if I put a 1 into there, the answer is 3. Thank you. And if I put in a 4 into here, the answer is 6. Awesome. So what we want to do here, wrong class, back to like 6th grade or something like that. If we want to do the opposite, real quick here, ready? If we want to go to the opposite of addition, what we do is we go like this. It kind of looks funny at first. Or we change it around. X is equal to y minus 2. Notice it's the opposite of addition. Notice also that your x's and y's on your table just got switched. So notice what happens here. If I plug in a 2 for the y, it gets me 0. Plug in a 3, 1, a 6 gets me the 4. Are we good? So we're doing the opposite of our operation, which switches my x and y to go backwards. We're doing a backwards way here. Okay, so let's do this here. Opposite of multiplication. And boom, that's cool. Like this, x and y here. We'll do 3 of them. And I'm just going to quickly go 0, 1, 4. Easy enough. Hey, that's easy. 0 is still equal to 0, huh? Boom. That's a 3. That's a 12. To go the opposite way, we got ourselves, see if this makes sense. Are we good there? That's the opposite way. Let's do one more, taking powers, because it kind of gets it. Because those two we understand easily, but taking powers gets a little bit more complicated. If I have like this, y is equal to x to the 2nd power. X and y. Let's see, 0 is going to be there. 1, let's keep it the same here. Everybody okay with, let's say 0, 1, and 16? Okay, now notice on this one's going to be kind of weird. Look at this. We were able to do an addition, right? Or we were able to do subtraction. We did one thing to one side, one thing to the other, right? Here we divided both sides by 3. Here, we can still do the same thing. It's kind of funny, but we add, well, we make a special symbol, right? It's a funky little symbol. Looks like this. That's my symbol, right? We put in a symbol, and we say to ourselves, oh, the answer is x is equal to square root of y, right? So we use a symbol in order to get to the other side. And we say, hey, that's going to undo this. Are we good? Now, thinking caps on, let's go. Y equals a to the x. That's our exponential function, is that right? Oh. Anybody see a problem?
Can't take a square root because it's x.
Yes, this symbol does not work anymore because you don't take squares because the variable is actually in the exponent. What do we do? Okay, you guys ready? we make a symbol. And the symbol's kind of funny. It was invented by a French mathematician. His name was Napier. And he said, we're going to change this up. And it's profound, because really, at this point, math is stuck. Math is stuck because we have no way to sort of go to the other side. He says, I'm going to just make this little symbol. The symbol is going to be LOG. And we're going to put a little A in here. A is going to be it's called a subscript. And then we're going to put a Y on this side, and we're going to call this X. So let's see how this works. So Y is equal to 2. Let's go 2 to the X power. We know we've done that before. So 0, 1, 2. 0 in here gets us any number to the 0 power is 1. 2 to the 1 power is 2. And 2 to 4. Okay. So now let's switch it around. So it's going to be log base 2, we call it a base 2 of Y is equal to X. Whoa, okay, so let's go with the meaning here. Ready? So 1 has to somehow go to 0, 2 goes to a 1, and 4 goes to 2. Let's see what the meaning is. Ready? Question is, log base 2 of 1 means this. What exponent do you put on 2 to give you a 1?
0.
A 0. So 1 goes to 0. It's going to take a little bit to get used to. That's fine. So I'm going to go to the next one here. Log base 2 of 1 is equal to what? Or, I'm sorry, 2. Sorry, I was in. That's the 2 I need. Whoa, that did not sound good. What exponent do you put on 2 to give you a 2?
1.
A 1. So 2 goes to 1. Eventually. So one more. Log base 2. It gets a little easier here though. Log base 2 of 4 is, what exponent do you put on 2 to give you a 4? 2. Hey, it's getting easier. Hold on. Let's do another one. Log, forget this for now. Log base 2 of 16. What exponent do you put on 2 to give you 16? 4, because 2 times 2 times 2, or we can go a little bit smaller here. What base do you put on 2 to give you an 8? 3. What base do you put on 2 to give you a 32? 5. Log base, oh, I'm going to change the base on you guys here real quick here. Log base 3 of 9. 2. Hey, this is so cool. Okay, we're good there. Does that make sense? We did these right here. That was pretty easy, wasn't it? At least for some. Oh, we got one more to go. 525. Log of base 5 of 25 is 2. We good? Okay. So let's.
5 squared, not 5.
Yeah, 5 to the 5th power. That's big. Okay, let's jam. Let's do the first 2, 3 examples and see how far we get. So what we want to do is just kind of get to the point of just changing forms one to the other. We good? Just real quick here, write it down if you need to. Now we can start writing down. So example 1. If you want to write it down, we'll go for it. Example 1.
Is that log 3?
It's log base 3 of 81 is equal to 4. That's true. That's a true statement.
Are we just writing
But we want to write it from one form to the other. That's what we're doing. So I'm going to write the equation on top. It's log base A of Y is equal to X. And that translates into, going both ways, of Y is equal to A to the X. So we have to be able to sort of work from one form to the other and backwards and forwards. So notice where your A's are. A becomes your base on your exponent. The Y becomes what's equal to, and the X, which was it equal to, becomes the exponent itself. Are we good? Sure. The A is the base. So the subscript for the log becomes your base in your exponential equation. The y value that's inside the log now becomes what is the value. So what's the value of the equation itself? And x, which was the value, now becomes the exponent. All right, another way to see it, my trig teacher taught me here. It's like a small little hook when you write it. You go from here to here to here. So A, take the x and equal to y. So base is 3. X is 4, x is 4, equal to 81. Is that true? 3 to the 4th power. 3 times 3 times 3 times 3 is 81. Boom, we're good there. Okay, can you guys do the next one if you have not done it yet? Sure. Log base 8. So again, you're just converting the forms, right? This one we'll actually get to know. So look at this, log base 8 of 4 would be 2/3. That's okay. We'll get to know there. But we're just switching forms now. So my base is 8. Exponent is 2/3. And value is 4. Done. We're good? Yeah. Exercise 2, let's go. We'll finish off with this one here. Can you write the exponential form in logarithmic form? So can you write that equation going backwards here? Yep, sure. Yep, please look at that. Sometimes the symbols, oh, you know what? That's why. I finally figured it out. Couldn't figure it out in trig class today. It goes into like pin mode for some reason. And so it doesn't have my little zoom in button. Let's see if this will work. Yes. Oh yeah, now it's cool. Cool. All right. And if you need to write it over again, that's fine. So this is log base A of y is equal to x, converts into y is equal to a to the x. Perfect. Log. This is I think the easier one. You just say, what's my base? What's the value? What's the exponent? Good there. What's my base? My value? And my exponent. Boom, done. Let's see, I think we have time for the next one. Let's do one more example just to sort of get it. And I took these exactly by the homework, so you guys can at least start your homework, because I didn't want you guys waiting to start the homework here. So once we finish this section, I'll tell you how much you guys can do of the homework. Should be pretty easy, right? And I want to follow it right away. All right, we've got 2.5 minutes left. So one more problem, go exercise 3. See, it does that. Okay, if I use my evaluate the function at the indicated value. And this is going to be pretty easy. You'll see this. This is what we were doing earlier. It says without using a calculator though. So we have to do it by hand. So we have a function now. Function is log base 16 of x.
16 to what exponent?
Yeah, let's bring in the
what exponent gives us 4?
16. What exponent do you put on 16 to give you a 4? Oh, not so fun. So in our minds, we're thinking this right here, right? If we say this guy is going to be, 4 squared. Good there? Now those are the same. Hey, that's what we dealt with the exponents there. 16 is actually 4 to the 2nd power. I'm going to use an x right over here just because it's variables. These guys are gone, so I'm solving for this. 1/2. Are we good there? So real quick in our minds, we should think of this. A half in the exponent really just means square root, right? Because in square root of 16, 4.
Oh, yeah.
So this guy's just 1/2. Okay, 2 more problems. Let's go. And we got 20 seconds. So 10 in there. Oh, notice this guy does not have a base. There's no base here.
Not that 10.
Base is 10. 10 is the default for base of logs. And we'll see why next time here. So what exponent do you put on 10 to give you a 10?
1.
1. Okay. Ooh, and the fun part. B to the negative 3. Okay, log base B of B to the negative 3. What exponent do you put on B to give you B to the negative 3?
Negative 3.
Negative 3. Of course. Because that would make sense. I'm going to just go real quick here, review back to what we've done already with logs, just so see them, and maybe we can develop some rules here as well. So let's jam with it here. So H, I know you guys already did it. This turns out to be a log base 16 of 4. And as we thought about it, if we want to change this around, what this really is saying is, what exponent do you put on 16 to give you a 4? That's what that is really saying here.
Oh, yeah. Yeah. Somewhere on there. Okay.
Okay, in this case, it's going to be, this will be more like 4 squared to give you 4. No, it's not going to be 4 squared. It's going to be, if you change, let me do it the other way because it'll be easier here. If you change this to 4, yeah, to the second power. Sorry, class, 1 second here. This will be trying to figure out what would be best to do it. It would be more like this right here. And this is technically a 1 here. So if this is 4 to the second to the x. Good there? And then we have rules for exponents. This little 2 times x makes 2x. That's still a 1. Once the bases are the same, we can solve for exponents now. And our answer is 1/2. Ooh, that's a lot of complications to do, huh? As opposed to if we just kind of think about what exponent you put on 16 to give you a 4, and then we sort of start thinking about, okay, well, that's going to be it's not going to be a 2, because that'll square it, and 4 is a square root of 16, so it has to be a 1/2, because 1/2 would give you the square root of something. We're good? Is in the exponent. Okay, so keep that in. This one, log base 10. So one thing we probably should mention in just a second here is whenever you see log by itself, if there's no base whatsoever, it's a base of 10. And this guy is going to be what? Just a 1, right? Because you're asking yourself, what exponent do you put on 10 to give you 10? It's just a 1. So I got this little rule we can start doing already here. See if this makes sense. I got a rule that will start off to the side here. Tell me if you guys agree or disagree. Log with the base of the base is equal to 1. True or false? So your book does it with A's here. So I'll put A's in here. Log with a base A of A is 1. Is that a rule we can accept? Okay, so then let's do this one here. This one is going to be log base B of B to the negative 3. What's the answer here? Everybody agreed with negative 3. What exponent do you put on B in order to give you B to the negative 3? I think that makes sense because the B's are the same, right? Therefore, the question mark is going to be negative 3. So I got next to a little rule. In fact, let's start writing these rules out on the side here. So rule number 1 that we just found out is log base b of b is 1. Then rule number 2, log base b of b to the x is x. See if that makes sense there. That's rule. Let's do this. I'm going to put some examples on the side, and we'll on this side, and we'll do the rules on the other side. So, Owen, answer to this guy. Too fast, too fast. Log base 5 of 1 is, Owen says 0. I agree, because what exponent do you put on 5 to give you a 1? Like, oh yeah, that's right. Any number to the 0 power is 1. Everybody good there? So next rule, log base b of 1 is equal to 0. Let's see if I can trick Owen. We good? We're gonna do a trick Owen day today. D 5 log 5 of 125.
Well, ignoring the 5 at the beginning, that's 25, but then we're raising 5, it says 125 again?
Is it 125 again? What do you guys say? Agree or disagree with Owen? Yeah, let's do this here. So let's do this part only. Let's do this part right here only. What exponent do you put on 5 to give you 125?
Oh, no. Wait, that's multiplication. Yeah.
It'd be 3, huh? Because 5 times 5 times 5 is 1. Okay, so that's the case. You got 5 to the third.
Still 125.
And then what's 5 to the third power? What do we do? Okay, can we write this as a rule? So a to the log base a of x. Okay, see if that makes sense.
And then it would be
It just equals x. We're good. Boom. Perfect. Okay.
Can you just like chain these and do they just work? You just keep going, like log a of x to the a to the log a of x. Does that still equal x? How far can we go with this?
I'll let you think about it.
No. I don't think it works anymore.
Just one, right?
So this is all.
Just one iteration. That's it. And the other one that we have to sort of think about is this one right here. I'll just add it in here. So log base 10 of x is the same thing as log of x. So there's that. And maybe, let's see, one more. Let's see. How about this? One more for Owen. Log base a of x. Ooh, tricky one. How about this? Log, it has to be the same base. What does that reduce down to? Isabel beat you to it here. It'll be x equals y. So this, how we write it is this right here. It says if that's true, then x is equal to y. And we should write that as a rule here on the bottom here. So log base a of y is equal to log base a of x. Then x is equal to y. I want to number these here. So 1, 2, 3, 4, 5, and 6. Okay, so you guys will see those properties somewhere in your textbook as you do these here. Sometimes as we start solving equations in 3.4, we'll have to use them as well. And 3.3, it actually is going to be all about more properties that we have with logs. This is just the beginning. Okay, so let's just try a few problems here. So example number 4, use the properties that we just learned to to simplify these expressions. I'll do really quick as well, just to, you guys are smart enough, you guys will know the rules there. That's 1.5. Log of 1.5 to the 1. And then that little 9 there is the base, and then log 9 is in the exponent. Log 915 is in the exponent itself. So we got to do that. All right, as you guys are doing that, let me check something out real quickly here. There it is. That's better. That is funny. Huh. Okay. All right. Should pick on people. I love picking on people here. So, anybody in row 1, Abe or Maddie? Log 1.5 of 1. 2/3.
1/3. I'm at
I think it just might be there. That's right. That's right. Whenever you see, that's rule number 3 right here, right? When it doesn't matter what base is, if you're taking the log of a log base of 1, it's just going to be 0. Boom. We're good. Anybody in row 2? Owen or Charlie? 9 log 9 of 15. 15. Awesome. Okay, that is rule number. Let's go back. That is rule number 4. That's this one here. Boom. Okay, we're good there. Just rules. You guys will see more of them on the homework here. Okay, what we want to get to is the graphing part of it here. So now the question is this: what does a log function look like? What is it actually on a graph? And so what we have to do is we have to actually graph 2 to the x first, and then we'll have to graph a log of 2. But once we get log of 2 down, we'll kind of know how the rest of them work. We're good? So this x to the second and log base 2, these guys are called inverse functions. We're good? Remember how we define them? What we did is we took the x and the y and we solved it for the other variable, right? We switched them around. So it's the switching of the around of them. So let's go this way here. I'm going to go x and f of x. And do we know what 2 to the x looks like? Anybody can tell me some important points for 2 to the x? What was that one very specific point all of them go through? All the way back to 0, 1 is perfect. Yep, 0 goes through 0, 1. Boom. Okay, if not, we can make a table. That's cool. I usually like for these guys make a table from -3 to +3, and that'll at least give me an idea of what this looks like. 2 and 3. Boom, now I get to bug people here. Landon, 2 to the -3.
I'm totally blanking on that.
Yeah, no problem, no problem. I'll help you out. So that little negative stumbles people here. That's going to be a reciprocal. It's going to go like this. Then that changes to a 1/2. And now you got 2 times 2 times 2 on the bottom.
2 times 2 times 2 on the bottom is 8.
8, perfect. It is 1/8. Good there. And Dylan on next one on the list here. Dylan, 2 to the -2.
1/4.
1/4, yeah, it's 1/2 squared. Eventually 1/4. Boom. Isabel, 2 to the -1. 1/2. Dylan, you get the easy one. 2 to the 0 power.
I think that all speaking.
But what is 2 to the 0 simplified? What is the simple form of?
Should just be 0,
Hmm,
1.
1, that's right. Yeah, perfect.
Sorry.
Yep, no problem. I'll do this one. 2 to the 1 is 2. 2 to the 2 power is Annette. Awesome. 2 to the 3rd power is 8. I'll stop there. Can we make a little graph just real quick here with these dots? So I'm going to go back 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to extend my little graph this way. And we'll make our little dots here. And once we do the graph for log base 2, we should kind of know how to do the other ones here. Okay. So we'll go from there. All right, you guys talk to me. Everybody finished off their graphs already? So -3, it's going to be up 1/8. It's barely above the x-axis. At -2, it's 1/4 of the way up. At -1, it's halfway to the 1 marker. At 1, it's at 2. At 2, it's at 4. At 3, it's at 8. So graph that goes like this, right? Flat for a little while, then all of a sudden it starts booming up. Oh, bummer. What did we forget? The horizontal asymptote. Right here. Comes across here. It's a dashed line coming across. And this guy is y equals 0, right? That's my horizontal asymptote if you want to label them. Okay, jamming. We did this already. This was a 3.1, no problem. For the log function, here's what we have. We have the replacement of x's and y's going the other way. That's what we have. So instead of -3 1/8, it is 1/8 -3. -2 to 1/4 now becomes 1/4 -2. 1/2 -1. 1 0 2 1 4 2 8 3. So there's my graph now. And again, we want to just do one of them here. 8. This is gonna be fun graphing this guy here.
If it's in the log function, do you always have the function that whatever the other one is?
No, as we get used to the log function, we should be able to do it right from the log function. But this is just to get us there. And so we'll do the next one, not going back. Even though some algebra textbooks actually they teach it that way. So then you don't ever graph the log function explicitly. Like, that's too easy. You guys can learn it. So let's jam. So first things first is, we're gonna go, look at this, this is crazy. We're gonna go 1/8 away from 0 here. And we're gonna go down 3. So we're just gonna scooch just a little bit over 0. Now we're gonna do it again. So 1/4, now we're gonna go just 1/4 away from 0, and we're gonna go down to -2. All right, how about this? We're gonna go halfway between 0 and 1 and bring it down to -1. All right, 1 0. Oh, these are easy now. 2, 1, 4 up to 2, and all the way out to 8. We finally get up to 3. Whoa. Okay. So here's my graph. I am super close to the y-axis, and then I've got to turn like that. Jamming. Oh, awesome. That's what I was going to say. Like, what are we missing? Can't say horizontal asymptote. There's a vertical asymptote here. So this one right here, put these little dash lines coming straight down like this. And this is now gonna be x is equal to 0. Okay, so here it is, what we got. We have vertical asymptote at x equals 0. And let's see how we can kind of put these together here. This important point is now, hey, this one is now 1, 0. We good? This guy became 2, 1, but what's the 2? 2 is our base, isn't it? So I'm gonna write it like this. I'm gonna write it as A1. Good there? It's my base, whatever my base is, up 1. This one was 4, right? This is, if we want to do this one, usually if you get these two right, you're done. You get down. Maybe a third one down here, like this one right here. This one right here would be 1 over A, negative 1. Okay, are we good there? Oh, let's do it. So let's try this. Let's try this real quickly here. I'm going to try it with, let's try it. I have 4 in here, but I'm going to change it to 3 here. So let me. There, that's what I want. Okay, based upon what we know here, we're good? So we're not going to go from here to here anymore. We're going to see if we can just graph it like this. So can we graph a y is equal to log base 3 of x? And using those critical points there, just need 3 of them. If we get 3, we got the rest. So 1, 2, 3, 4, 6. Why am I doing 6? No reason whatsoever. Just kind of a nice setup for my graph. Okay, let's jam. What point it's going to go through? Abe, all yours. Give me a point it's going to go through. 1, 0. Dun, 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 dun. 1, 0 is a point it's going to go through for sure.
Not log 3 or log.
Say again?
Not log 3 or log.
Log 3. Log base 3. Maddie, give me another point it's going to go through because we have a base of 3. No problem? And you can kind of think about what's going to happen here. If we plug in because some of these you can plug in. What's that going to give you? If you plug in a 1, you're going to get out a 0. Oh, that's that one already. That's that one there already. No. How about this? If you plug in a 3, there you go. That's what I wanted. Plug in a 3. Sorry, I couldn't hear because of the motorcycle. 1, absolutely. So the next point is 3, 1. So 1, 2, 3. We're going to go up 1. And notice if we were to square this, 9 is already too far out, right? Unless you have a graph that goes up to 10, right? Like, oh man, how about this one here? Ooh, this was a toughie. Owen, that one. He said -1. You guys agree with -1? Because 1/3 technically is a reciprocal of 3, right? Oh, cool. So we have this third point. Is 1 over 3 is -1. So it's a third of the way down. Once we get those 3 dots, we're pretty much set. We good? So then we go like this. We don't need to have an exact form. Can you ever do an exact graph? I'm not sure. Even calculator have pixelated for us here. Okay, Jen, is that good? Can we work with that now? Okay, you guys do. Now we get some fun stuff here. Okay, can you guys do this one here by yourself? Log base 4. Boom. Charlie, give me a point when you're ready. Once you're ready, move it down. 1-0, perfect. Lennon, give me another point when you're ready.
4-1.
4-1. 1, 2, 3, 4, perfect. And Dylan, another point when you're ready.
1
1 word, -1. Boom. Done. That's it. Isabel, what are we missing? Awesome. And done. Okay. That was pretty cool. Of course, that's just the beginning though.
But would we not do vertical acceleration then?
Yeah, I put it in. Vertical stop right here. That's where it ends. And now, do you guys remember how we did transformations? Remember how we scooted the graph sideways, right? And sometimes we scooted up and down. Well, guess what? We're going to do the same thing with these guys. No, I'm going to see the homework. Let's see how complicated it gets on the homework just to make sure. Okay, so let's jam. So this is the way the book, let me put it right over here. I'm adding to this slide here. This is the way the book has the graph here, just for us to consider all these things here. So the regular old log function, it has a domain. It doesn't work in the negatives. There's no such thing as log of a -3. Doesn't work. It doesn't even work for 0. You can't get log of 0. You can only get positive answers into that log function. So the domain is from 0 to -infinity, or 0 to infinity. The range could be anything. X-intercept, we already graphed this 3 times. It would say this graph is always increasing. It's going up forever and ever and ever. We say it's also 1-to-1. You don't really need to write all these down here, but I just want to just show you, just kind of look over here. We want to write down the transformations here a little bit. We do have a vertical asymptote. The y-axis is that vertical asymptote. We call this continuous because we don't ever have to lift our finger off a sheet of paper to graph the line. So it's continuous. And also, if we ever wanted to, oh yeah, so it is a reflection of this the exponential function. We talked about the switching the x and the y's. Okay, we're good there? This is also inside your textbook here, so if you want to refer back to it, so you don't have to take the time to write it down. It is on page 232, just so you can kind of refer back to it here. Okay, now let's jam. See a few people writing it down. Go for it if you want to. Cool, awesome. Okay, I think we're good. Everybody good now? Let's jam with transformation. So write this down. Transformations of this stuff. So y is equal to a log base b. So b's are going to be our log function right here. And it's going to be, do they ever multiply the x by something? No. Okay. No, it's the parentheses and it's inside the log. It's the log function inside there. All right, so remember transformations, right? Moving it sideways, moving it up and down, and reflections here. So let's do the reflections part here first. If, the first dot, if A is negative, what that means is we have a reflection about the x-axis. We don't ever do y, yeah, we do, that's right, okay. There it is, sitting there, okay. Boom, next. If x is negative, we have a reflection about the y-axis. Okay, good there. And we'll jam with some stuff here. So if, there's two parts here. If c is less than 0, we, remember this is the funny one. Remember, if it's less than 0, we move off to the right. If it's greater than 0, we move off to the left, right? It's always going backwards than what it, moves here. So if c is less than 0, it moves or shifts right. C greater than 0, it shifts left. Are we good there? Okay, and last one here, if D is less than 0, it shifts down. If D is greater than 0, it shifts up. There it is. Okay, got all the transformations here. Let's try one. So example 6, we've got to do a few things here first, but we'll do all of them, but we'll do it in terms of transformation here. So eventually, before we graph, we want to know domain, want to know the x-intercept, all the vertical asymptotes, and then sketch it. Oh yeah, sure. And to the directions themselves, let's see. Let's see how far I can put it in. Dave, is that good like that?
Yeah.
Just like get all of it in. Oh, okay. So the zooming in stuff, I may cut off the line a little sooner here, just so I can make the.
So it's going to shift to the right one.
Perfect. Okay. So guys, it is it's log base 3, and all it is, we just shifted everything to the right 1 unit, right? So off to the side. It's almost like easier to do the transformation in your mind first, and then do all the stuff. So here's a transformation. Oops. You guys talked to me whenever we finished copying it. Yeah, good. Okay, good. Boom. Okay, so the transformation is shift 1, 2, thank you, to the right. That's what we have on our hands. Boom. So in your mind, or on a sheet of paper, let's graph it and then we'll sort of see it. So x to the third. So let's see, it's shifting over to the right. Who can I bug? Isabel, go for it here. So if you need to go back to your log base 3 graph, that's fine. But there's an important point that all of them go through anyways, right? 1, 0. So if we shifted everything over to the right 1 unit, we got ourselves 2, 0. There's my first point. Boom. Dylan, bugging you now. Let's see, base 3. That means the previous point would have been at 3, 1.
Maybe 4, 1.
4, 1. So 1, 2, 3, 4, 4, 1. All right. And the other Dylan. Let's see. The previous graph would have been at 1/3 -1, right? Ooh, this is a toughie here. Where would it be at now?
1, 1/3.
Ah, couldn't trick you guys. No fun. 1 1/3 -1. We're good. There's that. So now the graph goes up like this, almost straight up, turns, curves, and done. And we have ourselves, now we can really graph this vertical asymptote now. Okay, now let's answer the questions here. What's my domain? Abe, what's my domain for this function? Okay, so the domain for log functions, they're anything greater than 0 or parentheses 0 to infinity, right? Now that we shifted over 1 unit this way. 1 to infinity, perfect. X-intercept, they always go through 1, 0. Now that we shifted over to the right, Maddie, are we okay with 2? And vertical asymptote. Owen, can you label the vertical asymptote for me?
1.
Or x equals 1, yeah. Boom, boom, boom.
You have to put x equals 1 for it to count on the test.
Yes, it does, because vertical asymptotes are equations of graphs. So you have to have that, as opposed to the x-intercept, you could just write 2. So there's a difference. Good question, very thoughtful question there. All right, now let's talk about it here. Let's see, would it have been easier almost to do the vertical asymptote as well first? Because you know it's shifted over to the right. Vertical asymptote starts at y equals, or x equals 0, right? We could have done that first based upon where the vertical asymptote lies, then you do the rest of it, and that would work too. Okay. I think we're good. Let's see, we got what, 10 minutes left here? So we got to the graphing section. That's cool. Let's see, we're going to introduce the natural log in just a bit here, but I wanted to do this whole, let's do this here. Let's jam with this. I'm going to stop there. Let me go to this little piece right here. We've got some videos. I think they're going to take less than 10 minutes here. Then we're going to introduce the other concept here. This is it log manipulation? Yeah. So the question of the last time in class was the whole concept of why are logs, what are they used for? Remember the table of who's the guy that invented logs again? Guy named Pierre, something like that, right? Yeah, sounds French. Okay, so he invents logs, but I want to just kind of let's jump to why were logs invented in the first place, and then what preceded our graphing calculator. All right, and how do we use them here? Well, so
I'm going to be talking about logarithms to the base 10. So, for example, if I have a number which is 100, I can think of that as 10 squared or 10, to the power 2. So 2 is the logarithm of this number, 100, to the base 10. 1,000 is 10 to the 3. This is the logarithm, the 3.
You guys agree, okay?
And it corresponds to the number of zeros there. It is logarithm of 1,000 equals 3. I can do 10 to another number. So for example, 10 to the 1.6232 turns out to be 42. That means that if I were to take 10, that means that the log to the base 10 of 42 is 1.6232
Are we okay
to
with
four
that?
significant figures. The reason it's useful is multiplication. If I have two numbers and I want to multiply them together, it's easy to make mistakes because there are a lot of little operations that have to be added up. If you go through logarithms and you get a logarithm of a number such as 42 and you multiply it with another number such as 37 or 59 or 200, you get the logarithm of that number and you add these numbers together. Let me show you an example. 37 times 59. Now I can write 37 as 10 to the 1.5682 and multiply that by this number, which is 10 to the power 1.7709. And when I multiply these numbers together, all I have to do is add this number to that number to make this into 10 to the 3.3391.
That's like a shortcut.
Yes, instead of multiplying numbers, you're adding this to that to get this exponent. And that number, it turns out, is 2183. Instead of having to write this out longhand as 37 times 59 and work it all out in gory detail, which will require 9 times 7 and 3 times 9 and then 5 times 7 and working it out and not making a mistake, all you have to do is addition, which is much easier. And if I were to do division, I would do subtraction, which is much easier. Addition and subtraction are much easier than multiplication and division.
Okay, we're good there.